So the parallel binary adders are used to add the sequences with more than a single bit. So if you have the, for example, the binary sequence with 2 bits or 4 bits or 8 bits or 5 bits, when you want to add them together, you need a parallel binary adders. So how to create a binary adder? Just combining the full adders. So for example, if you want to create a 2-bit adder, then all you have to do, you just add the two full adders together. Okay, so let's see the example. So let me go to the next slide here. Okay, 1 second. So this is a 2-bit adder. So what's happening here is that we have the two full adders, full adder 1 and then the full adder 2. So this 2-bit adder can add the sequences with 2 bits length, right? So for example, if you have the sequence like, in this case, let me change the color. So for example, in this case, the A, for example, A is equal to, for example, 1, 1, okay? And then the B is equal to, for example, 0, 1. So you want to do the A plus B. So what's happening here is that the A plus B, right? So let's do this. So A equal to 1, 1, and then the B equal to 0, 1. Okay, so we add this together. So these two bits, right? So the rightmost bits, they will go to the rightmost adder. So in this case, the A is equal to 1, B is equal to 1. So 1, 1 will go here. Okay, so we do the 1 plus 1. So 1 plus 1, if you remember, the output will be the 1, 0, right? So in this case, we have the carry bit because when you add the 1 plus 1, there's a carry generated. So this carry will go from the output of the first full adder and go as an input to the next full adder. So this one will travel from here all the way up to here and comes here. Okay, but you have the least significant bit already. So in this case, the result from the 1 plus 1 is 0 here. So 0 is already here. Okay, next what's happening is that we have the A2 and B2. So in this case, the A is 1, B is 0. So A is 1, B is 0, and then we have the incoming carry. So we do the 1 plus 1 plus 1. So again, the result will be the 1, 0, right? So sum will be the 0, and then the carry will be generated. So the result will be here. So 1, 1 plus 0, 1 will be equal to 1, 0, 0. How did we get this? By combining the two full adders together. Okay. Now, pay attention here. In this case, the least significant bit or the rightmost bit, in this case, the input carry is just connected to the ground or it's equal to 0, right? So this is just a ground symbol. So let's look at this in the circuit verse. So by the way, I will share the link to the circuit verse so you can go here and you can just play around and see how it works. So this is now we have the 2-bit adder. So you can see here I said that this is a 2-bit adder, right? So this is a 2-bit adder. Okay, and these are the inputs: A1, B1, A2, B2. This is the in my case this one is the least significant bit, and this is the most significant bit. Okay, so A1, B1. So if you have, for example, something like 0, 1 plus, for example, the 0, 1. So this 1, 1 here will go here. So 1, 1 will go here, and this 0, 0 will go here. 0, 0. Okay, so when you do the 1 plus 1, so from here, let's try this. So when you do the 1 plus 1, 1 plus 1, as you can see, the sum is equal to 0, right? So we can write it here. So this is equal to 0. And then here, as you can see, the carry is generated because it becomes the light green. So this means that the carry has been generated. And then we do the 0 plus 0 plus 1. And this will be result in a 1. Okay, so you have the 1 here and 0 here. So 0, 1, 0, 1 is equal to 0, 1, 0. Okay, now, as I said, in this circuit verse, this app, you can actually use this adder. Once you create the adder, you can use this inside the other circuits. So I put this circuit here. So let me see that this is a 2-bit parallel adder now. As you can see, this is 2-bit parallel adder. So this is my input A. A is equal to, in this case, 0, 0. B is equal to 1, 1. Okay, so you can see the output. Output is 1, 1, 0, right? So what's happening is that, so I have the A, 0, 0, plus B, 1, 1. So the output will be 1, 1, 0. right? So this one is least significant bit. So least significant bit means that this bit here, and this is the most significant bit, this bit here. Okay, so 0 0 plus 1 1. You can play around, you can change the numbers. For example, instead of the 0 0, you can do the, for example, 1 0 plus 0 1, right? So 1 0 plus 0 1. So again, you can try. So 1 0 plus 0 1. So output will be 1 1 0, and this is the result, 0 0 1, right? So 0 0 1 0 0 1. Okay, so this is a 2-bit parallel adder. And how did we create this 2-bit parallel adder? If you pay attention, right? We created it using the by combining the, if you double click, you can see we created the 2-bit parallel adder by combining two full adders. So this is full adder number 1, this is full adder number 2. How did we create the full adder? If you double click, we created the full adder by combining the half adders. How did we create the half adder? If you double click, we created the half adder by combining the multiple basic logic gates. So as you can see, just combining the logic gates, very simple logic gates, we can go towards the more complex and complex circuits. Okay, so from this basic logic gates, from the we created the half adder. From the half adder, we created a full adder. From the full adder, we created a 2-bit parallel adder. From the 2-bit parallel adder, we can create, for example, the 3-bit parallel adder. So this is now the example of the 3-bit parallel adder. So we have this is 2-bit parallel adder. This is a full adder. By combining these two together, now we have the 3-bit inputs, right? So this is A now can have the 3-bit input, and B also can have the lengths, 3-bit lengths. Okay, so you can actually again try this here. So this is a 3-bit parallel adder. So we have the inputs A1, A2, A3, B1, B2, B3, and then the Cin. But in this case, Cin is connected to the ground, right? So now we have the A is equal to 0, 1, 0, B is equal to 1, 0, 1. So when you add them together, you get this result. So you can actually test this again. For example, A is 0, 1, 0, B is 1, 0, 1. So you add them together, you get the 1, 1, 1, 0. So sequence is 0, 1, 1, 1, here, 0, 1, 1, 1. And you can play around by changing the numbers. For example, 1, 1, 0. And let's add these two numbers together. Try again. So A is 1, 1, 0. B is 1, 1, 1. Okay. So 1 plus 0 is 1. Now 1 plus 1 is 0, but we have the carry here. So 1 plus 1 is again the 0, but we have the carry, so result will be the 1, 1. So 1, 1, 0, 1, this is the final result, and you can see the result here, right? So 1, 1, 0, 1. So we created the 3-bit parallel adder. How? By combining if you look, you double click, you can see inside, we combine the 2-bit parallel adder with a full adder. And you can go and see the inside of each circuit. And similarly, you can create a 4-bit parallel adder. So in this case, we have this adder, it takes the 4 bits, right? So we have the 4 bits. So A is now the 0, 1, 0, 1, B is 0, 1, 0, 1, and then we have here we have the 2-bit parallel adder plus the full adder. You can actually implement the same circuit by using the 2-bit adders. Okay, so you can combine using the 2-bit adders. In this case, I used a different approach. I used the 1 3-bit parallel adder and then 1 full adder. It's up to you. Or you can just implement it using the 4 full adders. Just combine the 4 full adders together and you can get the same result. So it's up to you. But if you double click, you can see inside is the same circuit, right? Okay, so this is a 4-bit adder. Again, I go here. So this is the 4-bit adder, how it looks like from the outside. So you double click. This is how it looks like inside. And this is how it looks like from the outside. So this is the sequence A, right? So let's try changing the values. And you can see the different results are generated. So what's happening here is now, again, we have the A is equal to, in this case, the 1, 0, 1, 0. B is equal to 1, 1, 0, 1. So 1, 1, 0, 1. Okay. So by adding them together, we got the result. 0 plus 1 is 1. 1 plus 0 is 1. 1 plus 0 is 1. 1 plus 1 is 1, 0. So result is 1, 0, 1, 1, 1. 1, 0, 1, 1, 1 is generated here. So now you know how to create for example, this is a 4-bit adder. You want to go further? For example, this is now the 8-bit adder. So it's a bigger circuit. So let me erase this. So this is now the 8-bit adder. how did we create the 8-bit adder? By combining the two 4-bit adders. So this is a 4-bit adder, this is another 4-bit adder. This is our input sequence. Sequence is 1 0 1 1 1 0 0 1. B is 1 0 0 1 1 1 1 0. Okay, now if you look, first 4 bits are going inside the first 4-bit adder, right? So this first 4 bits from the A and from the first 4 bits from the B are going inside this adder here. Okay, so this adder here, and then the next 4 bits, so this next 4 bits and these next 4 bits are going inside the next 4-bit adder here, right? So you look, it's going here. Okay, and then the carry from the first 4-bit adder here, that this is the carry, is going as an input to the next 4-bit adder. Okay, so this is how now you can create a 8-bit adder. Okay, so again, if you look, it looks complex, but when you look inside of each circuit, it's just created by combining the what? Very simple basic logic gates, right? In the beginning we had the just simple logic gate. So this is a 8-bit parallel adder. Let's go back to our slide. So this is 3-bit adder. 1 second. Okay, so this is a 4-bit adder, right? So this is 4-bit adder, and the 4 bits is called a nibble. So just some term for this 4 bits is called nibble. Okay, and this is how it looks like from the inside. As I said, you can implement the 4-bit adder by combining the the 4 full adders, right? So you have the 1 2 3 4 full adders, add them together, attach them together, and you have the 4-bit adder. And this is a truth table for the 4-bit adder. And this is the actual fixed function device that you can buy. So this is the existing device, you can buy it, and this device adds the what? This circuit adds the 4-bit sequences together. So these are the input A, this is input B, and this is output. So this is carry in, this is a carry out. Okay, and by combining the two 4 bits, so for this is a 4-bit adder, this is 4-bit adder, by attaching them together, you can create a 8-bit adder that we did here, right? So this is the same circuit. So we have the 4-bit adder here, another 4-bit adder here, and this is the result. So the first 4-bit adds the first one adds the first 4 bits, another one is another 4 bits, and this is the final result. Okay, and you can actually test this. So this is just the question. What is the answer here? You can just test this answer by using the adder inside the circuit verse. Okay, so this is one of the practical examples where you can use the adder. So this is a voting machine. So you know the polling machines, when you have the like general election or any kind of election, you have to now count the number of votes for example, yes or no. So in this case, you have the 1 2 3 4 5 6 polling booths, right? So you go inside the polling booth and choose the yes or no. So as you can see, all of this is created just using the adders. So these adders are used to count the number of votes, yes or no. Okay, so just a very simple device. It counts the number of yes and no votes. And you can try to implement this for your final year project. If you want to do this project, just make sure that other students don't do this. But if you want to implement this, you're welcome. You're most welcome. Okay, so next we're going to talk about the ripple carry and look ahead carry adders.